Let us switch over to problem number 12. A plano-convex lens of refractive index 1.5 and radius of curvature 30 cm is silvered at the curved surface. Now, this lens has been used to form the image of an object. At what distance from this lens an object be placed in order to have a real image of the size of the object? Real image is supposed to be formed. Size of the image is supposed to be equal to the size of the object. When will that be possible? First of all, you have to recollect. When object is placed at the center of curvature of the convex lens, then we can understand the image formed over there will be real, inverted, having the same size as that of the object. That is a condition what he is asking us, at what distance it is to be placed, so that the real image formed over there will have the same size as that of the object. Options are given this way. First option is 60 cm, second option is 30 cm, third option is 20 cm, and fourth option is given as 80 cm as such. What is the correct option out of it? First of all, try to recollect. It is a plano convex lens like this, which of course is silvered. Silvered on what side? It is silvered at the curved surface. That's concave side. That is the other one. So this is now silvered according to him. Then you can understand well, when I take an object here, the ray whatever is falling, it refracts and reflects, again refracts, so that the image is going to be formed at I. So, what would be the effective focal length of this combination? First of all, you need to know. What is the formula for effective focal length here? 1 by effective value of focal length is equal to twice the focal length of the lens. 2 by focal length of the lens. What for we have to take? Actually 1 by f1 plus 1 by f2 plus 1 by f3. That is the formula. Out of that, twice it is crossing the lens there. Once it is refracting here, once it is again refracting here. So 2 times we have to take that value, 2 by focal length of the lens plus 1 by focal length of the mirror. But all of you know very well, 1 by focal length of a plano-convex lens when we talk about, that is going to be mu minus 1 by r. According to lens maker's equation, that's what is called lens maker's formula. Focal power P is equal to 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2. According to that equation, we can write 1 by focal length of the lens as mu minus 1 by r, that into 2, plus focal length of the mirror in terms of its radius of curvature, you write r is equal to twice f. Then f automatically becomes r by 2. So we can write this one as 2 by r. Now what is the ultimate formula? You just look at here, this becomes 2 mu minus 2 plus 2 by r. So simply speaking, twice the refractive index by the radius of curvature. That is reciprocal of focal length. Look at the value of refractive index given in the problem. It is given 1.5 and radius of curvature is given as 30 centimeter. So directly you write this way, twice 1.5 divided by 30. This now becomes 1 over 10. So what will now be the effective focal length of this system now? It is 10 centimeter. But he is not asking you the focal length. where should you place the object so that its real image is formed with the same size as that of the object. So that means you definitely can understand distance to the object. If I take distance to the object, this distance now should be equal to radius of curvature. Radius of curvature is nothing other than twice the focal length. So it now should be 20 centimeter because focal length is already calculated as 10 centimeter here. So twice 10, that now becomes 20 centimeter as such. That is going to be the distance to the object from this plano-convex lens. So what are the options given? Of course, I have given earlier. The third option exactly is 20 centimeter as we have got just now. Therefore, the answer for this particular problem is going to be C as such. So only thing you need to understand, whenever a plano-convex lens is silvered towards the convex side, in that combination you will find 2 refractions and 1 reflection. 2 refractions will take place and 1 reflection takes place. So accordingly, you have to calculate the resultant focal length of the combination. 1 by f is equal to 2 by focal length of the lens plus 1 by focal length of the mirror. If you just take up this, you directly can get the value of f, and after that the distance to the object is supposed to be twice the focal length, then automatically that becomes 20 centimeter. That is the concept. So this is problem number 12 for us. Check the next number, that is problem 13. A point object is placed on the principal axis of a convex lens of focal length 20 centimeter at a distance of 40 centimeter to the left of it. The diameter of the lens is 10 centimeter. If the eye is placed 60 centimeter to the right of the lens at a distance h below the principal axis, then the maximum value of h to see the image will be how much? The options are given this way. The first option is given 0. Second option is given 5 centimeter. Third option is given 2.5 centimeter and fourth option is given 10 centimeter. Actually, what he is describing in the problem, let me just show you in the form of a small diagram there, a small figure. If you look at, this is a convex lens he is talking, the very first one. This is its principal axis. There is an object that is placed, he is talking, where the object is placed on the principal axis. At what distance it is placed? At 40 centimeter to the left of that lens. So let us consider this the object. This, of course, the line of separation between two plano-convex lenses, like I can imagine. This distance is now given as 40 centimeter. And focal length of this lens is given as 20 centimeter. So the moment you look at these two values, immediately you can come to a conclusion. That object is placed at the center of curvature. Then surely the image also is going to be formed at center of curvature only. The image size and object size both are going to be equal numerically. So these points one has to get to mind first of all. Now here the ray whatever is just striking, it now just forms the image here. But what we are doing in this case, in this problem, the eye is kept somewhere here at a distance, say h below the principal axis. That is what has been mentioned there. So certainly you can understand in this particular case, this particular distance now is going to be 40 centimeter. And we know very well the total diameter, that means if I just take the ray is just striking at the edge like. That ray once again just goes through this one and just the final image is going to be formed somewhere here. This final image is formed here. Our eye is now here somewhere. This is going to be the height what he is asking for. So what we can understand here, you see, this distance becomes now the radius. Diameter is given 10 centimeter. Then automatically the radius of that one will now be 5 centimeter. So I can take this distance as 5 centimeter here. And at what distance the eye is kept now? Eye is kept at a distance 60 centimeter from the lens he has given you. Out of that 60, this is 40 we know. Then what will now be the remaining distance? Surely 20 centimeter. Now just look at this triangle and this triangle. Both the triangles are similar ones. When two triangles are similar, according to mathematics, the corresponding ratios of their sides can be equated. So what is it you are going to get? You check now. This side by this side is equal to this side by this side. Let us write h by 40, h by 20. Just look at this one. H by 20 is equal to 5 by 40. This side by this side is equal to this side by this side. Mathematically, when two triangles are similar, we can just write their corresponding sides equal. The ratios of their corresponding sides equal. Then automatically this goes 8 times. So what will now be the value of h? The question, 20 by 8. That of course will now be 2.5 centimeter. So what you can understand from this one? The moment an object is placed at a distance which is twice the focal length of the lens, its image also will be formed at the same distance on the other side of the lens. That is true. But our eye is not kept here now. It's kept below this one, below this principal axis, at a distance 60 centimeter. That is what has been given in the problem. That means the rays which are being converged here, once again they diverge and your eye is somewhere here now. At what distance it is placed now? 60 centimeter. Then this distance we know it as 40, then automatically this becomes 20. So taking these two triangles which are similar by nature, I have estimated the value of h as 2.5 centimeter. What are the options given? First option 0, second option 5, third option is 2.5 centimeter and fourth option is 10. Then automatically we can write the answer for this one as C. That gives 2.5 centimeter as the depth or the distance below the principal axis where you can keep your eye to see the image clearly. That is the concept. So this is problem number 13 what has been given. One of the good models, you people just should understand that these two distances are equal here, nothing more. Check the next number, that is problem number 14. The plane faces of two identical plano-convex lenses, each having a focal length of 40 centimeter, are placed against each other to form a common convex lens. All might have understood what exactly he is talking about. Two plano-convex lenses, he has taken them. This focal length is given 40 centimeter, this focal length is given 40 centimeter. Both are now pressed one against the other so that we get a complete convex lens like this of certain focal length. Now what is he talking? The distance from this lens at which an object must be placed to obtain a real inverted image with magnification equal to unity is how much? Magnification is 1. That is the condition you need to understand out of this problem. Magnification, for it to become 1, object should be placed at the center of curvature. Then automatically we can get the image also at the center of curvature on the other side of the convex lens. Since image distance and object distance are equal, magnification becomes unity. That is the concept. And what are the options given? 80 centimeter the first option, 40 centimeter the second option, 20 centimeter the third option, and 16 centimeter the fourth option. What is the correct option? We have to judge. Check this one. These two are now pressed this way. Then you can all understand well, when the focal length of this part is 40, this part is 40. What will now be the effective focal length of this one? That now becomes 20 centimeter. How can you judge that? 1 by F effective is equal to 1 by F1 plus 1 by F2. When lenses are made in contact with each other, that is the formula what we people used to adopt. 1 by effective focal length, that is equal to 1 by F1 plus 1 by F2. It's 1 by 40 plus 1 by 40, that now becomes 2 by 40. Obviously, the effective focal length of the lens, thereby formed by pressing them against one another, that is going to be 20 centimeter. Fine. But what is his question? Where should you keep an object from this lens so that the image formed over here will be having a magnification 1 unit? Magnification is 1 means what? Object distance and the image distance are supposed to be equal. When will they be equal? When this object distance is equal to twice the focal length, then image distance also will be equal to twice the focal length. So what is this focal length? We just have to take up. This is now called effective value of focal length. Therefore, distance to the object. Distance to the object we just want. That is now twice the effective focal length. What is effective focal length? We have already got 20. So this now becomes 40 centimeter. So where should you keep the object from this lens so that the image formed over there will have magnification unity? That is the question that is asked, and the distance is supposed to be equal to twice the effective focal length, which of course comes to be 40 centimeter in this problem. And this answer is just given as the second option for us in the problem. So we can say the correct answer for this one is the second option, which is 40 centimeter according to the calculated value. So this is the method you people have to adopt, and you need to remember that formula for the combination of lenses. Okay, so by any chance if the lenses are separated by a certain distance, there is a different formula. 1 by F effective is equal to 1 by F1 plus 1 by F2 minus X by F1 F2 we write, where X is going to be the distance of separation between the convex lenses or concave lenses, or one convex and one concave, no problem. So these are the points you have to remember for solving this problem number 14. Check the next number 15 please. An equiconvex lens of glass of focal length 0.1 meter is cut along a plane perpendicular to the principal axis into two equal parts. The ratio of focal lengths of new lenses formed will be. The options are 1:1, second option 1:2, third option 2:1, and fourth option 4:1. First and foremost, you should get to your mind in how many ways we can cut a lens. Generally speaking, you can cut this lens along its principal axis. That's one way of cutting the lens. If you cut this one like this, you get one portion of the lens like this, the other portion of the lens like this. But in this cut, if focal length of the original lens is f, then focal length of each part also will be f only. So this cut of the lens will never change the focal length of the piece what has been obtained there after cutting. Whereas, as given in this problem, the second way of cutting the lens is along this line, which of course is perpendicular to the principal axis. When you cut the lens like this, you will be getting two plano-convex lenses like this. This is one plano-convex lens, this is the other plano-convex lens. When you cut this one into two, you will be getting two plano-convex lenses like this. If I say the effective focal length of the original lens as f, this one will have a focal length 2f and this one will have a focal length 2f. You can easily guess how come. If you once again press them one against the other, 1 by 2f plus 1 by 2f now becomes 1 by effective focal length of the resultant lens. That comes to be f only. So when you cut the lens this way, this will be 2f and this will be 2f. So according to the problem given, focal length of the original lens is given 0.1 meter. Then automatically this becomes a 0.2 and that becomes a 0.2. You need not write the values and all. What is the ratio of their focal lengths? That is the question. This is f1 I take, this one is f2 I take. What is f1 is to f2? That is the ratio. So automatically we can write this one 2f is to 2f, which now becomes 1 is to 1. Only thing you need to understand in this particular case is when we cut the lens this way or this way, ratio of focal lengths will be 1 is to 1 only. But individual values will differ in this particular case. If you take here, if you cut like this, focal length of the original lens and the lenses thereby formed, both are going to be equal. Whereas when you cut it this way, each lens, that is each plano-convex lens, will have double the focal length of the original lens as such. So 2f and 2f, that ratio he is asking 1 is to 1, which of course is given as the very first option in the problem as such. So the correct option for this one is simply 1 is to 1 for the problem number 15, what we have to remember. Check the next number, problem 16. The focal length of a convex lens is f. An object is placed at a distance x from its first focal point. It is not u he is giving. Object distance usually be taken as u. But he is not giving directly the value of u. He is talking about from the first focal point, the object distance is x. That means you can definitely understand the object distance in this case is f plus x, that is the concept. The ratio of the size of the real image to that of the object is how much? Ratio of size of the image to the size of object. You can all understand what he is asking. He is asking you magnifying power or magnification. What are the options given? F by x square the first option, x square by f the second option, f by x the third option, and x by f the fourth option. So what is he asking? You have already got. It is magnification he is asking you. That is nothing other than f by f minus u. There is a direct formula for magnification in terms of object distance and focal length. Same formula is valid for a concave mirror also. Here we are talking of a convex lens, nothing special. But all of us we can understand in this case, u is equal to f plus x. U is equal to f plus x. That is what actually we know according to the problem provided to us. Therefore, magnification is equal to f by f minus f plus x. You can now rewrite the same this way, f by f minus x. This f getting cancelled, you are now left with f by x with a negative sign. So what exactly the ratio he is asking, you see, ratio of the real image size to the size of the object. That is nothing other than magnification. I just have got f by x with a negative sign. That negative sign, as far as magnification is concerned, you all in fact know well, when the image formed over there is real, magnification will be written with a negative sign. When the image formed over there is virtual, then automatically we can write the magnification with a positive sign. So in this particular case, that negative sign indicates that the image formed over there is real. Thereby, what is the ratio? Ratio is nothing other than f by x. So f by x now is exactly the third option which has been provided to us in the problem number 16. So you can directly take f by x as the value there. Only thing you should recollect once again is magnification in terms of focal length and object distance, that is f by f minus u. That is the concept one has to remember. So this is problem number 16, for which the option is C. That is the third option, which is f by x with a negative sign. Negative sign indicates that the image formed over there is real. That is the concept. Check the next number 17, please. An object is placed at a distance of 15 centimeter from a convex lens of focal length 10 centimeter. On the other side of the lens, a convex mirror is placed at its focus such that the image formed by the combination coincides with the object itself. That is the condition he is mentioning in the problem. Final image formed by the combination is coinciding with the object itself. Right. Then what is the question he is asking? The question is, the focal length of the convex mirror is how much? Convex lens he has already given. Its focal length is given 10 centimeter. Object is placed at 15 centimeter distance. Everything is known to us. Now, the options are given this way. First option is 20 centimeter, second option 10 centimeter, third option is 15 centimeter, and fourth option is 30 centimeter. So let us first of all check the same condition over here. There is a convex lens this way. This of course is the line of separation what we people used to take, and this one is the principal axis. Now he has just given us there is an object placed at a distance 15 centimeter from a convex lens of focal length 10 centimeter. Focal length is given 10 centimeter here, and object distance is given 15 centimeter here. That is the value of u. And what else he has given you? He has kept a convex mirror. Where it is kept, try to understand from the problem carefully. A convex lens is placed at its focus. At its focus in the sense, this is the convex mirror what we are having now. It is placed at the focus of this convex lens. That means this distance will now be 10 centimeter. This is the convex lens what has been given, and this one is the convex mirror what he is talking. Now what we can understand out of it, you look at. Suppose a ray is just falling this way, another ray this way from the object. This of course refracts like this. This refracts like this, fine. After refraction, the image is just going to be formed somewhere here. Even this ray also goes there. Wherever these two rays are just merging right with each other, there the image formation that takes place due to the convex lens we can understand. Now the question here is where this image is being formed. First of all, we have to understand that where the image is going to be formed. We know U is given 15 centimeter and F is given 10 centimeter. What is the image distance we just have to take? So we can write 1 by V is 1 by F minus 1 by U. If I just take this one like this, 1 over 10 minus 1 over 15. So this now 31 time. So V is going to be 30 centimeter now. 30 centimeter must be from this particular optic center to that point. So you certainly can understand this distance between the optic center and this image formed, that is going to be 30 centimeter. So probably you all might have got this point. The image is formed there. Imagine for a while this mirror is not placed. Then definitely the image would have been formed there. But now the condition what he is giving, you incorporate to this situation. Final image is coinciding with the object. When will that be possible? When this distance is equal to its radius of curvature, then the ray whatever is falling here, it retraces its path, it falls normal to the plane and reflects back along the same line. It again refracts along the same line. Then finally the image is going to be formed here itself. This is the final image which is in coincidence with the object. So what we should understand, unless this distance is equal to the radius of curvature of this convex mirror, it is not possible for us to find the final image coinciding with the object. So what we should understand, this total distance is 30, this distance of separation is 10, then what will now be the remaining distance here? That now must be 20 centimeter. And what should be this 20 centimeter? That must be its radius of curvature. So according to the calculation, radius of curvature of what? Of the convex mirror. Of the convex mirror. If I take that one as R, that must be 20 centimeter according to the calculation what we have made. If R is to be 20 centimeter, then focal length of that concave mirror, this convex mirror, that must be half of this value. So how much it should now be? 10 centimeter. So what is the focal length of the convex mirror is the question he is asking. So you can directly come to the conclusion, the focal length in this particular case of this mirror must be 10 centimeter. So according to the given options, this is in coincidence with the second option given there. First option 20, second one 10 centimeter, third one 15 centimeter and fourth one 30 centimeter. These are the four values given, and our calculated value of 10 centimeter is exactly given as the second option there in the problem. So one should understand the general construction here. What is the condition for the image to coincide with the object? That is very important here. This distance from this convex mirror to the first image that is to be formed by convex lens, that should be equal to the radius of curvature of this mirror. That now must be 20 centimeter. So when r is equal to 20, automatically we can write f must be half of that value, that is 10 centimeter. As such, this is problem number 17 what we have. Problem number 18 now. The distance between a convex lens and a plane mirror is 5 centimeter. Parallel beam of light is incident on the convex lens. After reflection from the plane mirror, the final image is formed at the optic center of the lens. Observe the condition carefully. Where the image is formed right now? The image is formed at the optic center of the convex lens. That is what has been very clearly mentioned there. Then what is he asking for? The focal length of the lens is how much? First option is given 10 centimeter. Second option is given 20 centimeter. Third option is given 40 centimeter. And fourth option is given 5 centimeter. What is the correct option out of the 4 we have to pick up? Let me first of all explain you, taking the construction there. Where is the object, where is the image, where is convex lens, and where is the that plane mirror that has been placed. Look at this one is the convex lens what has been taken. This one, okay, once again we shall take up this one as the line of separation of these two plano convex lenses. Like this one is the principal axis. This is the plane mirror which has been placed now. So this one is the plane mirror and this one is the convex lens. What are the specifications he has given? You identify first. Distance between convex lens and a plane mirror is 5 centimeter. It is now given 5 centimeter like this. Okay. After reflection from the plane mirror, the final image is formed at the optic center of the lens. That is the concept. And that too, what kind of a beam that is incident on it? You can surely understand the beam whatever is falling is parallel light, parallel beam of light. So you can say this one the parallel beam. Parallel beam of light, when it is incident on it, the image should be formed at the focus. That means the image distance must be equal to the focal length. That is what we know. But what is he talking about? You see here, this ray is now refracted. This also has been refracted. In true sense, both the rays would have been merged at this particular point like this to form the image. But what is happening now? This ray has been reflected this way. This ray has been reflected this way. Observe carefully. The ray whatever is just falling parallel to the principal axis, it is just striking the plane mirror, reflecting, and this ray also is reflecting. This ray whatever is going straight along the principal axis also reflects like this. All the reflected rays are now merged at one point. What is that point given in the problem? You identify where they are meeting now, at the optic center of the lens. So this is the optic center of the lens. That's what he is talking. So simply speaking, the rays when they are reflecting and forming the image at the C, can't you now understand this becomes the image distance for this mirror, please? Because actually where is the object? That is the object for this. That object is now supposed to be a virtual object for the mirror, that to a plane mirror. Then automatically it gives you a real image formed there. Plane mirror has a capability of forming virtual image of a real object and real image of a virtual object. Both will never be real. Both will never be virtual. So that is the point what we have to understand. Accordingly, you can say when this distance is 5 centimeter, this distance also must be 5 centimeter. There is no doubt absolutely in this calculation. Simple mathematical logic. What is that logic here? The image formed by the convex lens should become an object for the plane mirror. Where is the image going to be formed? Image will be formed at its focus. That is actual image 1. This is the image 2 what we are getting as the final image. You can now understand in this particular case, when this separation is 5 centimeter, thus that separation also should be 5 centimeter, and this total distance must now be equal to the focal length of the given convex lens. So what we can understand now? Focal length of the convex lens now must be 5 plus 5, it should now be 10 centimeter. When it is 10 centimeter, according to the given options, if you look at the very first option, that is given as a 10 centimeter. So first option itself is the correct option for this problem number 18. Only point you should remember is after reflection, the rays are being converged here. That means that is the final image which is formed as real there. Now the image formed by this one will be here. That image becomes an object for this mirror. So object distance and image distance are supposed to be equal. Therefore, when this is 5 centimeter, that also should be 5 centimeter. The sum of these two now should become the focal length of that convex lens thereby taken. So f can become now 10 5 plus 5, that is 10 centimeter. It should be 10 centimeter according to the calculations. So the correct option for this one is the first option, which is A. That is problem number 18 what we have. Check the next number, that is problem number 19. The distance between an object and a screen is 100 centimeter. A lens produces an image on the screen when placed at either of the two positions 40 centimeter apart. The power of the lens is nearly how much? First option is given 3 diopter. Second option is given 5 diopter. Third option is 7 diopter. And fourth option is 9 diopter. Firstly, you should understand what exactly this problem is based on. This problem is based on conjugate foci or conjugate foci. If you consider a convex lens here, what is going to be the minimum distance between an object and its real image formed by a convex lens? I repeat my question. What is the minimum distance between an object and its real image formed by a convex lens of focal length f? What is the minimum distance there? It should be, if its focal length is f, the minimum distance, right? Minimum distance between what? Minimum distance between an object and its real image. An object and its real image formed by a convex lens of focal length f, that is equal to 4f. Remember this result thoroughly. Minimum distance between an object and its real image formed by a convex lens of focal length f will be 4f. Suppose if I take this is the source and this one is the screen. if the distance between these two is greater than 4f, then what you find here, at two different positions of this convex lens, position 1 and position 2 I am writing. At two different positions of this convex lens, you can obtain an image of the same object on the screen. And these points are called conjugate points. When this is object distance, this will be image distance for this first position. When this is object distance, this will be the image distance for the second position. If I take this distance of separation as L, what is this L now? It is slightly greater than 4f. That's what actually we people are taking up here. This L we are considering. So greater than 4f, how much it is not necessarily be taken up like. It should be more than 4f, that is the condition. At least it should be 4f. That is the case. And if I say the distance of separation between these two positions as x, so x is the distance of separation between those two positions at which the convex lens is forming real image on the screen. And L is the total distance of separation between the source and the screen. Then what will be the focal length of this convex lens? L square minus x square by 4L. It is actually one particular method, we call it as conjugate foci method. In that method, we can estimate the focal length of the convex lens given. What is the formula that can be used there? L square minus x square by 4L. This particular problem is exactly based on the same method. Distance between an object and a screen is 100 centimeter. So he has given you the value of L as 100 centimeter. What else he has given? A lens produces an image on the screen when placed at either of the two positions 40 centimeter apart. That is now, according to this, it is x that is given 40 centimeter. Come on, estimate focal length and thereby focal power. So focal length, when we consider this one, it becomes now 100 square minus 40 square by 4 times 100, that is 400. So this one you can expand like a square minus b square. 140 into 60 divided by 400. 1 0 you can cut it off here in each. Twice 2 here, thrice 2 here. This goes 7 times. So you are getting 21 centimeter as the focal length. But in fact, I don't want focal length to be calculated in this problem. What is focal power? He is asking you the question. So focal power. P can be written as 1 by focal length taken in meter. You can directly write the same this way, 100 by 21. So it is nearly 5 diopter. Had it been exactly 20, we would have got exactly 5. It's 21 now in the denominator. Slightly less than 5 you will get, but he is also asking you the answer, nearby answer only. Nearly how much? Nearly it should be 5 diopter. 5 diopter is exactly the second option given over there. Therefore, the answer for this one will now be B. That is the concept. So what we should understand in this particular method is, what is the minimum distance between an object and its real image formed by a convex lens of focal length f? It will be 4f. So the distance what has been mentioned here as 100 centimeter, that must at least be equal to 4f. That is the concept you people should understand. Okay, so if you look at that one, it is more than that one means we will be getting, so that value of L as 100 and X as 40, L square minus X square divided by 4L, that gives you the focal length of that lens taken up. So your answer will be 21 centimeter for focal length, and corresponding focal power will now be nearly 5 diopter, for which the second option is coinciding with our answer what has been calculated here. So that is problem number 19 for us.